Hi friends, welcome back to our series of sessions on energy conservation and management. Today we shall discuss about steam boiler, the various energy saving measures. The various energy efficiency opportunities, as we call them, in boiler system can be related to combustion, heat transfer, avoidable losses, high auxiliary power consumption, water quality and blowdown. Examining the following factors can indicate if a boiler is being run to maximize its efficiency. The first one is the stack temperature. The stack temperature should be as low as possible. However, it should not be so low that water vapor in the exhaust condenses on the stack walls. This is important in fuel containing significant sulfur, as low temperature can lead to sulfur dew point corrosion. Stack temperatures greater than 200 degrees centigrade indicates potential for recovery of waste heat. It also indicates the scaling of heat transfer, recovery equipment, and hence the urgency of taking an early shutdown for water or flue side cleaning. Second one is the feed water preheating using economizer. Typically, the flue gases leaving a modern 3-pass shell type boiler are at temperatures of 200 to 300 degrees centigrade. Thus, there is a potential to recover heat from these gases. The flue gas exit temperature from a boiler is usually maintained at a minimum of 200 degrees centigrade so that the sulfur oxides in the flue gas do not condense and cause corrosion in heat transfer surfaces. When a clean fuel such as natural gas, LPG or gas oil is used, the economy of heat recovery must be worked out as the flue gas temperature may be well below 200 degrees centigrade. The potential for energy saving depends on the type of boiler installed and the fuel used. For a typically older model shell boiler with a flue gas exit temperature of 260 degrees centigrade, an economizer could be used to reduce it to 200 degrees centigrade, increasing the feed water temperature by 15 degrees centigrade. Increase in overall thermal efficiency would be in the order of 3%. For a modern 3-pass shell boiler firing natural gas with a flue gas exit temperature of 140 degrees centigrade, a condensing economizer would reduce the exit temperature to 65 degrees centigrade, increasing the thermal efficiency by 5%. Next one is the combustion air preheat. Combustion air preheating is an alternative to feed water heating. In order to improve thermal efficiency by 1%, the combustion air temperature must be raised by 20 degrees centigrade. Most gas and oil burners used in a boiler plant are not designed for air preheat temperatures. Modern burners can withstand much higher combustion air preheat, so it is possible to consider such units as heat exchangers in the exit flue as an alternative to economizer, when either space or a high feed water return temperature make it viable. Incomplete combustion can arise from a shortage of air or supply of fuel or poor distribution of fuel. It is usually obvious from the color or smoke and must be corrected immediately. In the case of oil and gas-fired systems, carbon monoxide or smoke, which is for oil-fired systems only, with normal or high excess air indicates burner system problems. A more frequent cause of incomplete combustion is the poor mixing of fuel and air at the burner. Poor oil fires can result from improper viscosity, worn tips, carbonization on tips, and deterioration of diffusers or spinner plates. With coal firing, unburnt carbon can comprise a big loss. It occurs as grit carryover or carbon in ash and may amount to more than 2% of the heat supplied to the boiler. Non-uniform fuel size could be one of the reasons for incomplete combustion. In chain-grade stokers, large lumps will not burn out completely, while small pieces and fines may block the air passage, thus causing poor air distribution. In sprinkler stokers, stoker-grade condition, fuel distributors, windbox air regulation, and overfire systems can affect carbon loss. Increase in the fines in pulverized coal also increases the carbon loss. Excess air control is required in all practical cases to ensure complete combustion. To allow for the fuel types of fuel, normal variations in combustion, and to ensure satisfactory stack conditions for some fuels. The optimum excess air level for maximum boiler efficiency occurs when the sum of the losses due to incomplete combustion and loss due to heat in flue gases is minimum. This level varies with furnace design type of burner, fuel, and process variables. It can be determined by conducting tests with the different air-fuel ratios. Now, the table shows the theoretical combustion data for solid fuels, which is bagasse, coal, bituminous coal, lignite, paddy husk, and wood. And theoretical air combustion data is for kg of air required per kg of fuel and kg of flue gas per kg of fuel, meter cube of flue per kg of fuel. Theoretical percentage of carbon dioxide in dry flue gases, percentage carbon dioxide in the flue gas achieved in practice. If you see the coal, kg or excess air common boiler is 10.8 kg of air is required per kg of fuel, whereas kg of flue gas is expected around 11.7 kg of flue gases. Then 9.4 meter cube of flue is expected per kg of fuel. Then theoretically, percentage of carbon dioxide in dry flue gases is expected to be around 18.7. And percentage of carbon in flue gas achieved in practice is it could be 10 to 13. 13 is the optimized temperature. Then for liquid fuels, we are seeing the furnace oil, which is most commonly used, which is 13.9 kg of air per kg of fuel. And kg of flue gas, it is 14.3, 11.5 meter cube of flue per kg of fuel. And theoretically, 15% of carbon dioxide is required in flue gases, whereas 9 to 14% is comfortably achieved. Typical values of excess air supplied for various fuels are given here. Then for pulverized core, type of furnace is completely water-cooled furnace or partially water-cooled furnace. Excess air could be 15 to 20% by weight. Then for coal, for different types of spreader stokers, water-cooled vibrating grate stokers, chain grate and traveling gate stokers, underfeed stokers, the excess air could be of the range of 30 to 60% by weight. For fuel oil burners, 15 to 20%, multi-fuel burners, 20 to 30% is the excess air required. For natural gas, it is very low, of 5 to 7%. For wood, it is high, 20 to 25%. For bagasse of all kinds of furnaces, 25 to 35% of excess air is required. Then controlling excess air to an optimum level always results in reduction in flue losses. For every 1% reduction in excess air, there is approximately 0.6% rise in efficiency. Various methods are available to control the excess air. Mainly, portable oxygen analyzers and draft gauges can be used to make periodic readings to guide the operator to manually adjust the flow of air for optimum operation. Excess air reduction up to 20% is comfortably feasible. Then the most common method is the continuous oxygen analyzer with a local readout mounted draft gauge by which the operator can adjust airflow. A further reduction of 10 to 15% can be achieved over the previous system. The same continuous oxygen analyzer can have a remote controlled pneumatic damper positioner by which the readouts are possible in a control room. This enables an operator to remotely control a number of firing systems simultaneously. The most sophisticated system is the automatic stack damper control, whose cost is really justified only for larger systems. So the next one is the radiation and convection heat loss. The external surfaces of a shell boiler are hotter than the surroundings. The surfaces thus lose heat to the surroundings depending on the surface area and the difference in temperature between the surface and the surroundings. The heat loss from the boiler shell is normally a fixed energy loss, irrespective of the boiler output. With modern boiler designs, this may represent only 1.5% on the gross calorific value at a full rating, but will increase to 6% if the boiler operates at only 25% of output. Repairing or augmenting insulation can reduce heat loss through boiler walls and pumping. Next one is automatic blowdown control. As we know, uncontrolled continuous blowdown is very wasteful. Automatic blowdown controls can be installed that sense and response to boiler water conductivity and pH. A 10% blowdown in a 15 kg force per centimeter square boiler results in 3% efficiency loss. Then the reduction of scaling and soot losses. In oil and coal-fired boilers, soot buildup on tubes acts as an insulator against the heat transfer. Any such deposits should be removed on a regular basis. Elevated stack temperatures may indicate excessive soot buildup. Also, same result will occur due to scaling on the water side. High exit gas temperatures at normal excess air indicate poor heat transfer performance. This condition can result from a gradual buildup of gas side or water side deposits. Water side deposits require a review of water treatment procedures and tube cleaning to remove deposits. An estimated 1% efficiency loss occurs with every 22 degrees centigrade increase in stack temperature. When the flue gas temperature rises about 20 degrees centigrade above the temperature for a newly cleaned boiler, it is time to remove the soot deposits. It is therefore recommended to install a dial-type thermometer at the base of the stack to monitor the exhaust flue gas temperature. It is estimated that 3 mm of soot can cause an increase in fuel consumption by 2.5% due to increased flue gas temperatures. Periodic offline cleaning of radiant furnace surfaces, boiler tube tanks, economizers, and air heaters may be necessary to remove stubborn deposits. Reduction of boiler steam pressure is also another alternative, which is an effective means of reducing fuel consumption, if permissible, by as much as 1 to 2%. Lower steam pressure gives a lower saturated steam temperature without stack heat recovery. Similar reduction in the temperature of the flue gas temperature results. Steam is generated at pressures normally dictated by the highest pressure or temperature requirements for a particular process. In some cases, the process does not operate all the time, and there are periods when the boiler pressure could be reduced. An energy manager should consider pressure reduction carefully before recommending it. Adverse effects such as an increase in water carryover from the boiling owing to pressure reduction may negate any potential saving. Pressure should be reduced in stages, and no more than 20% reduction should be considered at any time. Then we have the variable speed controls for fans, blowers, and pumps. Variable speed control is an important means of achieving energy savings. Generally, combustion air control is affected by throttling dampers fitted at forced and induced draft fans. Though dampers are simple means of control, they lack accuracy, giving poor control characteristics at the top and bottom of the operating range. In general, if the load characteristics of the boiler is variable, the possibility of replacing the dampers by a variable speed drive should be evaluated. And the next one is effect of boiler loading on efficiency. The maximum efficiency of the boiler does not occur at full load, but at about 2/3 of the full load. If the load on the boiler decreases further, efficiency also tends to decrease. At zero output, the efficiency of the boiler is zero, and any fuel fired is used only to supply the losses. The factors affecting boiler efficiency are, as the load falls, so does the value of the mass flow rate and the flue gases through the tubes. This reduction in flow rate for the same heat transfer area reduced the exit flue gas temperatures by a small extent, reducing the sensible heat loss. Below half load, most combustion appliances need more excess air to burn the fuel completely. This increases the sensible heat loss. In general, efficiency of the boiler reduces significantly below 25% of the rated load. As far as possible, operation of boilers below this level should be avoided. Next one is proper boiler scheduling. Since the optimum efficiency of boilers occurs at 65 to 85% of full load, it is usually more efficient on the whole to operate a fewer number of higher loads than to operate a larger number of low loads. And finally, boiler replacement is the one last option in energy conservation measures of steam boilers. The potential savings from replacing a boiler depend on the anticipated change in overall efficiency. A change in a boiler can be financially attractive if the existing boiler is old and inefficient, not capable of firing cheaper substitution of fuel, over or undersized for pressure requirements, not designed for ideal loading conditions. The feasibility study should examine all implications of a long-term fuel availability and company growth plans. All financial and engineering factors should be considered. Since boiler plants traditionally have a useful life of well over 25 years, replacement must be carefully studied. So these are all the simple measures, energy conservation measures involved in steam boilers. Hope you have enjoyed the session. Keep watching. Thank you very much.